if we represent the matrix product here as AX equals B, we see that this product 3, 5 times XY is going to equal 9. So that means 3x plus 5y equals 9, the same as our first equation. And the 2 negative 4 times xy equals negative 6. Gives us 2x minus 4y equals negative 6. That's the second equation. This system is then represented by this matrix. We leave out the xy just as we did before, and we understand that this system is equivalent to this system. This system is also equivalent to this system in the sense that the two equations represented by this system and the two equations represented by this system are completely equivalent. And we know that they're completely equivalent because we've done the whole thing. We've changed this to this using operations that keep the equations equivalent, to keep the system equivalent. Now, what does this represent? Well, in matrix terms, this represents this matrix times xy equals 3/11, 18/11. The identity matrix times xy is just xy, so we see that this matrix here ends up representing just the solution xy equals 3/11, 18/11. This is equivalent to what we said before, but we've represented it in matrix terms, and it looks a little bit different in these terms, and you should understand what we've got here. Okay, now finally let's take a quick look at what we do if we have a system of more equations. Okay, it's not always necessary to reduce to the identity. If we do, of course, we get some added benefits, but if we're just trying to solve a single system, often it's sufficient to simply reduce the system to what's called upper triangular form, and that's what we're going to see here. Very similar to what we did before. Now notice we have a system that represents three equations and three unknowns. The unknowns might be x, y, and z, or x1, x2, x3, and this is divides two sides of the equation, or separates the two sides of the equation, and these are the numbers on the right-hand side. Okay, so upper triangular form means we want zeros below the main diagonal. The main diagonal of this matrix on the left of the dotted line is the 20, 14, 12. Below the main diagonal we've got these three numbers here, the 10, the 5, and the 5. And we'd like to replace these numbers by zeros using operations that keep the whole system consistent with what it was at the beginning. In order to do that, we can write down the first row. There's nothing we really want to change about it to get the upper triangular form. If we subtract half the first row from the second, that'll get rid of the 10 here and make it into a 0, right? So we do the second minus half of the first, subtracting the first from half the first from the second. That's going to give us 0. Now, if we subtract half of 4 from 14, subtracting half the first from the second, we're going to get 12. Half of 4 is 2. Subtract that from 14, we get 12. Subtract half the first from the second here. Half of 4 is 2. Subtract from 5, we get 3. We do the same over here. Half of 500 is 250. Subtract from 850, we get 600. So following the rule, second minus half the first, in order to get the 0 here, we end up getting these numbers. And then we want a 0 here. Let's just do the same sort of thing, only we'll subtract 1/4 of the first row from the third and replace the third with what we get. So the third row will become third row minus 1/4 of the first. A fourth of 20 is 5. We subtract that from 5 and we get the 0. That's why we chose 1/4, so we would get the 0 there. A fourth of 4 is 1. Subtracted from 5 gives us 4. A fourth of 4 subtracted from 12 is 11. And a fourth of 500 is 125. Subtracted from 1,000 is 825. So following the rule, third row minus 4 times the first, in order to get the 0 here, we get the 41185. Now we've got a new system that's equivalent to the first, but there are no x's in this system. So this would be like 12y plus 3z equals 600, 4y plus 11z equals 875. That's a simplification because now the last two equations really form a system in two unknowns that we could solve for y and z. And if we had those, we could substitute those values back into the first equation and find x. Okay? Now we've got zeros here and here. Remember, we wanted one here also. So what are we going to do? Well, we've got 12 here and we've got 4 here. Let's subtract 1/3 of this row from this one. So we'll do the third row minus 1/3 the second. Notice that that's not going to hurt the zeros over here. We don't want to mess with these zeros. So we wouldn't want to subtract a multiple of the first row from the third. That'd be convenient because we have a 4 and a 4. But if we subtracted the first row from the third to get a 0 here, we'd get a -20 here and mess up that 0. We don't want to do that. So we use the second row to get the 0. So we do third row minus 1/3 of the second. So a third of the second is 4. Subtract that from 4, we get 0. Here, a third of this is 1, and subtract that from 11, we get 10. A third of the 600 is 200. We subtract that from 875, we get 675. So this is the upper triangular form of the system. Now, this says 10y equals 675. We can easily solve this for y. Get 67.5. Then this system says 12x plus 3y equals 600. If we substitute the 67.5 we got for y here into the 3y, then we're going to be able to solve for the x. We'll have 12x plus 3 times 67.5 equals 600. We'll easily get, I think I'm saying x, y. Again, that's 12y plus 3 times 67.5 equals 600. We solve, we get our y. Then we got an x and a y that we can plug into the equation represented by this first line. And not an x and a y and a z that we can plug into this equation. So we have a 4y and a 4z to plug in. And we'll have a 20x, and we'll have the 500, and we'll easily be able to solve for x. So once you have upper triangular form, you just use this, what we call back substitution, one equation at a time. You just climb back up row by row and evaluate the new variable in each row.